Hello students, so today we are going to program the problem we solved in the last lecture video. So we will use the Scilab. So if you search Scilab on cloud, you can find it. Otherwise you can actually install the Scilab. So you can search for it. So this is a Scilab page. From here you can actually install on your system. Yeah, it has all versions like Windows, Linux, Mac version, all of them, all versions are here. So this is also very similar to MATLAB also actually. So you can if you know the MATLAB, you will be very easily you can adapt to Scilab, and this is open source also. It's freely available, so that's why this is my choice. Also this is available on cloud as well. Okay, so this version you can install on your computer. From mobile also you can access, and for that you have to use the Scilab on cloud. So if you search on Google Scilab on cloud, so you will get some pages. So the one I'm going to use is cloud.scilab.in. Most likely this has been developed at IIT Bombay actually. So it has given the interface to Scilab actually. Yeah, so this is also good because I can access from tablet also, from cell phone also, you can, from a smartphone also you can access, and whatever you write here will be actually the solved on the server at IIT Bombay. Most I think it's IIT Bombay only. So what you see here is here Scilab code. Actually you can write something and this will compile here. So for example, let's say I want to write x. Yeah, so syntax is like a MATLAB only, as I told you earlier. So x let's say x equal to, okay, so x equal to, and then we have 1 to 10. This is how you write. Yeah, so like, yeah, so y equal to let's say we are just writing it. We can have a function sign, sign of x. Yeah, okay, and you can plot also. So let's say we say plot x comma y. Okay, so this is what I coded. Yeah, so this, so x equal to 1 to 10. Yeah, and then y equal to sine x, and then plot. Yeah, so now we can execute it. For executing you have to press on execute, and you will see the results. See, so what you got here is a graph actually of sine of sign, although our sampling is not good, meaning that we have very coarse, we have x 1 2 3 4 5, accordingly sin x we are getting not a smooth. But anyway, this is how the MATLAB also works. So, and here we got something there is some error and all. So, we will see if there is some error, then we can also switch to old Scilab Cloud, so which is here. Yeah, so you can see here old Scilab Cloud. So, if you we can also use that also. Okay. So, it has two versions. So, in case you are facing problem on the latest one, actually yesterday I was trying the latest, the Scilab on cloud, it had some problem. Then I actually tried the old Scilab on cloud, which is also in the on this page also, one tab is there. So, you can just click on old Scilab on cloud, and this may work. This is what this is. So, we can copy the same code, okay. Okay, so let's start working. Okay, so let's not waste time. So we will going to solve the problem. Okay, so we will start with the problem number is, our problem number is 5.3. So we can start with a comment. So double slash is comment. So let's write problem number 5.3. Okay, so that's what that is. Okay. Okay. So once we give some introduction, the problem number 5.3, that's what I wrote here. Then the problem has 4 nodes, as you can refer to the previous lecture video. So we have nodes, so we can write nodes equal to, so this gives you the node numbers. Okay, so node numbers are 1 to 4. So 1 to 4, this is how you write 1 to 4, 1 to 4. Okay, so this is 1 to 4. Okay, so that means it will make node equal to 1, 2, 3 and 4. Yeah. Okay, and then okay, so you can also check. I am going to press execute like here, and then you will see the values you can see here, right. So you can see here this is nodes equal to 1, 2, 3, 4. Yeah. So this is the result. So that means it is working. Okay. So nodes. Okay, and then if you write semicolon after the command, then you will not get this kind of output. This kind of output you will not get. So you can also check here. So let's here I am going to press execute again, and see in result section nothing is coming. That means just because you had here the semicolon, you are not getting anything here. Okay. Okay. Now let's move on. So problem number 5.3 notes we have 1 to 4. Similarly, we have elements. Okay, so elements also we have 1 to 4. So let's also we write. So we are just making the IDs basically. So elements also 1 to 4. So 1, 1 to 4, 1 to 4. Okay, so we will give the semicolon here as well. Sorry. Okay. 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 Now few constants. Let's write the constants first. The constants we are given. So we know that L, big L, it is the length of every member. So we keep it equal to L equal to 1 meter, right. So L equal to 1, we write a semicolon. We can also give comment, yeah. So comment we write length, length of, we understand what L is. Okay. Now next we had E equal 10 to power 11. So equal to 1, and then we had E 11. Okay, semicolon again, and then this is Young's modulus. Young's okay, so Young's modulus. Then we have area was given. So area is equal to, we had 2 times 10 to power minus 2. So 10 to the power minus 2. Okay, and this is the cross sectional area. So area of each bar. Okay. So it may be convenient to just calculate a small k. Small k just really means E over L only. So we will write E times A times divided by L. Okay. So this we can straight away use because this will be a common. Okay. So just we write, we are giving the comment also, we will say stiffness. Yeah, general stiffness. This is a stiffness for three members. Okay, the one which has 1 meter length. Okay, done. Okay. Now we move further. So far so good. Okay. So the next thing will be to calculate the stiffness matrix. Okay. So how will you do? We have to make a big K, and for doing that we need what is known as connectivity matrix. Okay. So for every element we need connectivity matrix. for every element there are two nodes which is joined by elements. So it's very important you just write connectivity matrix, okay, and how will we make we will refer to this as Ij, okay. So Ij equal to, this tells you that this is connectivity matrix, okay. So here we will start, we have the first element will have a connection between node 2 and 3, right. So if you see the node numbering in the last lecture, so we have first element connected to node 2 and 3. So we have node 2 and 3, yeah. So node 2 and 3, okay. This is the first entry, okay. Then second one is connected, the second one is connecting the nodes 3 and 4. So we will write 3 and 4, okay. Then third one, so we can also write like this also, okay. Let it be like this, okay. So first one between 2 and 3, second one between 3 and 4, third one between 4 and 1, right. So between 4 and 1, so we write 4 comma 1 comma 1, okay. And the last one, which is the diagonal one, right. So that connects node 2 and 4. So we write 2 and 4. So we have 2, 4, okay. Okay. So we can check it also whether everything all right. Yeah. So we have Ij recorded 2, 3, 3, 4, 4, 1 and 2 and 4. So that means we are ready with that, okay. Done, okay. So this connectivity matrix means for every element which all nodes it is connected to, that's what this is telling you, okay. So although we have said nodes 1 to 4 and element 1 to 4, probably we are not going to use this one, but this is just to reference that there are 4 nodes and 4 elements, just to, you know, we can also use that probably. So total, we just write it node numbers and node numbers and this element numbers. Okay. Okay. So once we have that, next is for every element we have to calculate the stiffness matrix, and accordingly we have to build the decay, right. Okay. So either you go by in a loop, actually more advanced programming will have some kind of functions in which we are calculating all those things, but today I am going to just do very simple programming, you know, so that you also follow the steps basically, and then you can go more advanced. Yeah. So then you can have different functions for doing certain kind of job, and that will be very a small program, but it can work. But today I am just purposefully making it lengthy, but it will this will also work basically. Yeah. So I will go element wise. Okay. So we will say element number 1. Yeah. So element number 1. Okay. Element number 1. We have calculated the k here, and the basic k we can build, you know. So we can say that the basic we can say ke, right, ke, right. So ke tells you for the very the basic one, from where we can rotate and we can make everything. So will be equal to k multiplied by ke, k equal to k multiplied by, and then as you remember, we had 1 comma 0 comma, right, 1 0 minus 1 comma 0 semicolon. Semicolon means we can it goes to the second row now. Second row was 0 comma 0 comma 0 comma 0. Then third row, yeah, third row is okay. You can also give a 3 dot here and continue in the, you know. So that way also you can, yeah, we can do like this. Then we had minus 1, yeah. So minus 1 comma 0 comma 1 comma 0, yeah. Then we have 0 0 comma 0 comma 0 comma 0, okay. And after that we have the we have to close the square bracket, and we can check it whether it has recorded so far or not. Okay. So execute it. Okay. So it has, you can see that it has worked. It says 2 0 minus 2 0. So that means we have this ke as the very basic one, and from there we can derive the all others. Yeah. Okay. So we can also have we have ke here, and for this is truss, right. So for every element we can also have the angle. So angle is the is one vector which will store the orientation of all the elements. Okay. So the first one, the first element is vertical. Yeah. So let's have this vertical. So we have 90 degrees. So we can write it as pi. I think here you have to give percent pi. So percent pi is the, this is how you write here. So what we can do is we can have in degrees actually, and then we can multiply them by some factor so that it is in radian. So, we will use the radian inside the sinusoidal functions, right. So, the first angle is 90 degrees, so we write 90 comma. Second angle is 0 degree, so we have 0. Third angle is again 90 degree. We are, since we are saying it is connected 4 to 1, remember. So we are so this is first element where we are saying that this is from 2 to 3. So 2 is down, 3 is up. So if you go from 2 to 3, it is 90 degree. 3 to 4, if you go from 3 to 4, you are going 180 degrees. So you have to write 180 degree, yeah, because this is how you are, the orientation is like that, yeah. So from the first one, if you go first element to the second element, how you are going, that you are going to define. So since in that problem you are going from third node to the fourth node. Okay, so I think let me draw, try to draw here the how they are connected. So it is something like here, right. So nodes are the 4 here, and then so let me comment this one. So you have 4 first, right, and then you have connected, then you have 3, right. Okay, and then you have let's use this. Yeah, okay. Like this one. And we have a number 1 here, and then number 2 here. So this is how it is organized, yeah, and that's why we are writing like that. So connection 1, we have 1, then 2 here, then 3 and 4. So connection is 2 to 3, then from 3 to we are going to 4, from 4 to we are going 1, and then we have from 2 to 4 as well. Yeah. So okay, so there is one more thing. So okay, so there is also bar from 2 to 4 as well. Okay, so although I have not drawn here, but there is a bar going like this as well, like this, yeah. Okay, okay, just for reference. Okay, yeah. So that means angle, if you see the first angle is 90 degree from 2 to 3, second angle is 180 degree 3 to 4, fourth angle is 270 degree, okay, and fifth angle is from 2 to 4, it is 135 degree. So accordingly we have to write. Okay. So 90 is not 0, second one is not 0. So 90, it is 180 degree. Then we have 270 degree, and after that we have 135 degree. Okay. So if you know the coordinates, you can also find out from the coordinates as well. So if you give x, y from in the software that you use, typically you draw something and from there x, y, it finds out everything. So it can find out the angle from there by itself. So advanced user should actually make that way. So so we have this angle vector. Okay. Okay. Okay, but yeah, so I forgot to multiply with pi. So pi divided by 180. Okay, so that is going to convert that into radian. Okay, so done. Angle is done. And here we can also, since angle is there, and angle we are going to use for making the stiffness matrix, and we have the rotation matrix R. So we will define the R. R is equal to, yeah. So okay, so how are we going to use R? Okay, so basically we are going to use there has to be a function basically which is going to use we will use the to find out the stiffness matrix. But the thing is we have to define the function first so that we can use it. So in order to define the function, you have to do in the beginning itself, yeah. Okay, or you can also have here also in the not in the beginning, at the end also you can have, no problem, as long as it is inside the same file, it should work, and we will try. Okay, so you can write a function. So let's say we are saying function, okay, function, and we are going to find out the big K of element, yeah. So K E, big K E, just a small K E. So we are, let's call K R rotated one. K R means rotated K of, or a small K R means rotated one instead of K E. Okay, so is equal to name of the function after that. So Kr is the basically the thing that is going to return, and function name is let's call it rotated K, yeah, rotated K, yeah, or simply rotate K, yeah, maybe rotate K, and let's have one argument that it takes, and that argument may be the angle it takes, right. So ANG angle, yeah, okay, and now we can write the function here, okay. We have R, or we are going to define everything. So anyway, so here we can say end function, it is 2. Okay. So, here we are going to make the rotation matrix here. So, then what we have, the rotation matrix as we know is rotation matrix we have sine, and then we have angle, okay, comma, okay, then we have cos, angle, okay, and then we have 0, comma 0, sorry, 0, okay, that's done for the first line. Okay, then we have it should have cos first and then sine. So, cos first and then we have sine. The second line we will have sine first, so editor is not I want to copy and all, so there may be some shortcut, but I don't know basically, so I am typing in all. In desktop it is much easier, but yeah, so the idea here is to just to do everything in front of you, so you understand line by line. So we have sine of angle, comma, and then we have cos of angle, then we have 0, yeah, okay, fine. So, we have 0 and then 0 again, semicolon, enter, okay, then we have again 0, comma 0, comma, and we are going to cos angle, comma, then sine angle, okay, semicolon, and okay, then again we will complete 0, comma 0, comma minus sine. So, we have minus sine angle, okay, comma, and then we have cos angle, okay, and then we close the bracket and give semicolon here, okay. Okay, so far this is what we have. So, let us see whether everything all right. We can just say execute and see if everything is fine. Okay, so far so good. Okay. Now once we have the rotation matrix, okay, so next thing we can, okay, just let's see everything now. So far it looks like this. Okay, so KE we can have the semicolon now, so that we don't see anything in the during the results. So we already know this is working. Okay, so we will execute again, just see, and it should not be there. So function we have, we made kr equal to uh, this function, so far we just got the rotation matrix only. So the next thing we have to write, we have to add the kr. Basically we have to build the kr, and for building the kr we will need to rotate the matrix, right. Okay. Now the so ke that we made, I think we have to transfer that to here. Yeah. So okay. So anyway, so we can have a function which also takes ke. Okay, so the function takes ke as well, so we can have a comma, we can have okay, so we'll have comma ke, so that we give the angle and also the ke, and it will rotate by multiplying with the this rotation matrix, and it will give me the final kr, right. So that means we write here k k e sorry kr, and kr will be equal to, and how we have to multiply, we have to multiply rt, right. So if you say just write r, and you will have the prime, that means the r quote, single quote, we call r prime, okay, so single quotation, or r. So multiplied by ke, whatever we are getting ke, and then multiplied by r. Okay, so this is how it was. Yeah, and this is going to make, so let's see whether it works. Okay, so let's just try to execute, just see if, okay, so far so good. Okay, so we can also check, so if we give for element number 1, okay, so angle is like this, for element number 1 we can find out, okay, so in bracket, so say element number 1, element number 1, and we can give k, let's call it k rotated one, right. So, k r 1 is equal to and what do we have? We have the function that we have to call. So, this becomes rotate rotate k, okay, and then angle we have to give. So, angle is angle angle 1, right. So, if you give angle 1, this should be sufficient, and comma ke, it will put the ke, and this should give us. So, if the function is working, we should be able to get kr1. So, let us see whether kr1 works or not. Okay. So, we are going to execute, press execute, and okay. So, undefined variable rotate k, okay. Okay. So, let us put the everything in the top, and then we will call. So, function we have to define before we call it. So, we can have that way also. So, let us have same function we are going to write after the function. So, return, let us call it angle, sorry, kr1 equal to rotate k and rotate k, and then we have angle 1 for the first element, comma ke. Let us do it this way. Let us run it now. Okay. So, okay. So, now you can see you are getting all the values here, right. It is working now. So, it is giving you the values after rotating it by 90 degree. What you see here is first one is almost 0, d means is a double precision, and this is 7.5 times 10 to power minus 24. So, it is very 0 basically. So, very small number. So, it tells you say is a small number basically, yeah, okay. And all others are, so first is insignificant, second term also if you see very small, third is also 4, this is also like this. Now, if you see 2 times 10 to power 9, okay, so that means this is a big value, this is a big value, this is a big value, this is a big value. So, we got the rotated one automatically, right. So, it is working. So, for the first element we got like this one, yeah, okay. Now, for the second one also you can do the same thing, yeah. So, kr2 you can find out, kr3 you can find out, or you can have a loop to find them and put in the k, okay. So, we will write one loop in which for all the 4 elements we are going to find out, call this function, and accordingly we are going to write the fill the global stiffness matrix, okay. So, let us make one loop here. and okay. So for writing the loop, we start with something like I equal to, right. So we can have I, we write for loop. Okay. So for I equal to 1 to 4. Okay. So in fact here 4 is, you can also write number of elements NE, right. So NE, okay. So where NE is equal to number of elements, we can write NE equal to, you can also NE equal to 4 we can have here, because number of elements is 4. So this is a 4. So we can have here number of elements. Yeah. Okay. So for 1 I equal to 1 to NE, and then what are we going to do? So we are going to write basically call this matrix, the call rotate k function. So we just write kr equal to angle and ith angle first. So it goes the ith angle, okay, and we get the kr. Okay. So once we get that kr, next will be to have the assembly of the big K. Okay. So we have to write the big K first. So we actually have the biggest stiffness matrix. So we define K, big K is equal to, and this is we start with zeros. So equal to zeros means all zeros, because we know that wherever we don't put anything it becomes zeros. So we will have all zeros, and we have degree of freedom total 8. So we 2 times, okay, so we will have 2 times number of nodes is 4. Similarly we can have number of n for number of nodes. Okay. So n is also 4. Okay. So we just write number of nodes. Okay, we give comment here, number of nodes, okay, which is 4. So we have k equal to zeros with 2n by 2n by 2n, okay. So we have just initialized the global stiffness matrix. So initialize the global stiffness matrix. Okay, that's what we did. Okay. Okay. So for I equal to 1 to NE, we have kr equal to, we can rotate it, rotated one we get. Okay. Once we have that, we are going to put this kr into the big K. And how will we put? We will do like this, K, and then we are going to put at some degree of freedom. Which one? So that depends on the node number, right? So if we have node number 1, then for connectivity matrix we have already there. So we have ij somewhere defined. So we have, see here, we have the ij here. So we know that if the ij is 2, 3, if the ij is 2, 3, that really means the degree of freedom will be 5, 6, sorry, node number 2 will have 3, 4, 5, 6. So node number 2 will have 3 and 4. Yeah, so if node number is n, the degree of freedom will be 2n minus 1 and 2n. Yeah, so degree of freedom, corresponding degree of freedom, we have to write, say if for element number 1, we first find out what is the connectivity matrix. So we have a small ij equal to big ij, okay, and then we find out which one, or we can have like this one, node 1, we can also write this, node 1 of the ith element will be ij, and the way we made it, we have the all rows represent the element number, right, in ij matrix, and hence the first row, for example, is 2, 3, then we have 3, 4, then we have 4, 1 and 2, 4. So row number 1 will have the information about the first element. So hence we can write, we will take the ith one, okay. So ij, ith one, so we have I, and when say 1, that means the ith row first column will give me the first node for this element, right, okay. So just write semicolon, and node 2 will be nothing but the ij, and then I comma 2 means second column. Ith row second column will give me the second node of that element. Which element? Ith element, the one for which it is iterating right now, okay. Now we are done here, node 1, node 2. So we know the degree of freedom, corresponding degree of freedom becomes, so we can write DOF, degree of freedom will be equal to which one? So this will be node 1 multiplied by 2 minus 1. So 2 multiplied by, sorry, not, I did not intend to do this one, okay. So 2 multiplied by DOF, sorry, node 1 minus 1 comma times node 1 comma 2 times node 2 minus 1 comma 2 times node 2 times node 2, and then close the curly close the square bracket, and we have the degree of freedom ready with us. Okay, so this is the degree of freedom where we have to put the kr into the big K. So we will write K, then DOF comma DOF, means in these rows and columns we can write is equal to, same thing we repeat, we have to add to whatever existing. So K DOF comma DOF and plus. So in addition to that, we are going to write plus what? KR. So whatever we received, we are going to add to the big K, and that's what we did. So we have finished till here. This was a for loop, so we are going to the K is automatically, all the K will be updated in the big K. Okay, so we have done already. We can check it. We can just write a big K at the end and see whether it compiles all of them or not. Yeah, so let's see. So execute. Okay, so if you see, we get the big K. So it has column 1 to 6 and then column 7 8. So we have all the, this is the big K which is compiled. Yeah, that means we got the big K. This is our global stiffness matrix. Okay, so we have got the global stiffness matrix. Next thing is to solve the problem, and for that we have to know the degree of freedom which are free, right. So we can also write here the free degree of freedom So, free degree of freedom, the one which is free, and what do we know about it? So, we have nodes which are free, are 3, 4. So, we have degree of freedom 5, 6, 7, 8. So, we write 5, 6, 7, 7, 8. Okay. Okay, my bad. I think something happened. Okay, so I will have to write it again. So free degree of freedom, free DOF is equal to we have 1 5 6, so we can also write like this 5 6 7 and 8. Okay. Okay. So without comma it should work. Okay. So although I have written in comma in all of them, so without comma in MATLAB it works. So here it should work like this. So or we can just check also. So let's check it whether it working. So yeah, so it's working. This way also it works. So semicolon we will put here. Okay, this is a free degree of freedom. So what we have to do? We have to solve it, and free degree of freedom. We have to make the force the u vector. Okay, so u vector with 5 6 7 8 1, right? So we have the no, u vector not needed because we are going to invert it. Force vector we have to find out. So force f vector where free f free DOF, right? So f at free degree of free degree of freedom, f at free degree of freedom means the nodes which are free to move, not fixed. So there we will have f free, let's write, and we have 10 Newton in x direction, then we have 0 Newton, then we have 0 Newton, then we have 0 Newton. Okay. So we are done here. Okay. 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 So once we have that, next is find out the x. Yeah. So let's say let's write capital X free means at the what is the not x but u means what is the value of u at the free degree of freedom system at the u where the nodes are free, that's what it means. So this will be equal to we have to invert the k. So inverting the k we can also write like this. So big K we write first, so big K, then in bracket we write free DOF. So free DOF comma free DOF. So that means I have removed all other degree of freedom, only free degree of freedom, only those degree of freedom which are free are included here. And then instead of writing forward slash we will give backward slash like this one. Okay, that really means k inverse, actually this means k inverse, and then we will have u. Yeah, so u and which one u not u but f, sorry, so we will have f free. Okay, so this is going to give us the displacements. Okay, so let's so here we can give a comment find displacement, find u, find unknown u, right, unknown u. Okay, so let's execute it and see how. Okay, so this is what is here. Okay, let's execute it, let's see what we get. So executing, you press on execute and see the results. Okay, so A and B must have equal of the row number of undefined. This is into the power of. Okay, so here it says that A and B must have equal number of rows. Okay, so so we did not have the equal number of rows. Why? Because there was some error. Always you check for error. So we have to give f free is we have defined as a row vector. So number of rows has only one. So we have to actually transpose. We have to give, say this is a transpose of f free. So we just have to say dash, right, f free dash, not dash but this upper single quote. So like this one, yeah, or f free prime. Okay, so now this this should work now, hopefully. So let's press continue and see. Yeah, so it has worked, and this is giving some values. If you see here, so u free is equal to 10 to power minus 15 multiplied by these values. Yeah, so that means it is telling you in x direction we have this value 1 2 3 4 5 6 7, 2 times 10 to power 7 multiplied by 10 to power minus 15. In y direction, in along the degree of freedom 6, there is a 0 movement, yeah, and for 1500 corresponds to the degree of freedom 7, and not 1500, this what is 15 times 10 to power 6. Similarly, if 5 times 10 to power 6 multiplied by 10 to power minus 15, this corresponds to the degree of freedom 8. Okay, so please refer to the figure in the previous video lecture. Okay, so we are solving the same problem but using the computer. Okay, so this is how you got u free. Okay, so that means we have the all the displacements now. So and you can accordingly you can find out all the other forces. And how can you find out? So you can basically you can complete total u, all u, and how you do that? You can have u equal to u, we can construct is equal to zeros, because most of them are zeros only, and we construct it like a number of rows will be 8, because 8 degrees of freedom. So 8 comma 1. Okay, we make like this one, out of which the free degree of freedom we know. So u, we can write u free degree of freedom, right, comma 1, means I am going to put whatever the value we got, we are assigning those value, and this is equal to u free, right. So we got that. Once we got that, next thing will be to multiply, we get the full F. So, total force vector including all the reactions and all we can find out, and F will be equal to simply whatever K we got and multiplied by U that we have compiled them. So, this is what the F is going to be. Okay. So, we have done. So, let us execute it, let us see whether it is working. Yeah. So, we get F, and you can see that the F values that gives you the minus, the first is first degree of freedom, we have 0 along x axis at node 1, we have 0. In vertical direction at node 1 we have minus 10 degree minus 10 Newton. At second node in x direction we have minus 10. At second node in y direction we have 10. At third node in x direction we have 10, which is given. Yeah, and the forces all other places are 0, we know that those are 0. So, they are close to 0, those values. So, you get all the forces automatically. Yeah. Okay. Okay. So, what you are saying, whatever we have done in the last lecture video, the same problem we have solved here. We have find out the displacement, we have found out the forces. Okay. So, force including the reaction forces. So, we knew just the force on the free degree the nodes where the we found out we knew the force only where the nodes were free, but where the nodes were fixed we will get the reaction, and hence you will get all the values, you know. So, all from top the 4 values are the reaction forces that you got.